This is what we'll build in this video, a model of Earth that we can rotate around the origin and smoothly animate between any two orientations. Specifically, I want to show how to use a number system from math called Quaternions to implement the core functionality that drives this visualization. To do this, we'll implement a class in Python which encodes the properties of the number system and demonstrates how Quaternions are used to rotate 3D objects. Quaternions are used in animation, robotics, and physics to represent rotations and orientations in 3D space. For example, Boston Dynamics' robot dog uses Quaternions as part of 3D transformations to describe itself, objects around it, and its understanding of the world. Quaternions are chosen for applications like this because they have several advantages compared to other methods for representing 3D rotations, like rotation matrices from linear algebra. Compared to rotation matrices, Quaternions are numerically stable, computationally efficient, and do not suffer from gimbal lock. In addition to their advantages, a big reason why I want to show how to rotate an object like Earth using Quaternions is their method for animating between two orientations. Visualizing how this method works fundamentally changed my understanding of Quaternions. It's a good example of how Quaternions are used in practice and showcases the powerful language they provide for rotations. In the last video, I explained the elegant method Quaternions provide for computing the transform position of a point. We'll use that method again here, but this time we won't spend as much time getting into the details of the fourth dimension. The primary focus of this video is a practical understanding of Quaternions and their relationship to rotations in 3D space. I should mention, this video does not cover how perspective projection visualizes 3D space, or how to draw the continents on Earth. These are interesting problems, but out of the scope of this video. And if you're coming from the previous video, I've changed the colors associated with the basis vectors, because most 3D software uses red, green, and blue for the X, Y, and Z axes. Finally, this video might be more interesting if you have a background in linear algebra or complex numbers. To start, let's talk about the primary features of this application. The first feature allows the user to click and drag the Earth to different orientations. The second feature allows the user to rotate between any two orientations of Earth. For example, let's say when the user presses the spacebar, we record the current orientation. Then, after they scroll around for a bit, they can press enter and the Earth rotates back to the recorded orientation. I want to show you how we can implement both of these features using Quaternions. But first, let's talk about the coordinate system of our setup. For this application, Earth is modeled as a sphere whose center is at the origin of the coordinate system. For now, I'm going to erase the continents and visualize the orientation of the sphere using these red, green, and blue arrows. We're going to talk more about these arrows in a little bit, but first we have a design choice to make. To make it appear as if Earth is rotating, we can either change the orientation of the sphere, or we can change the orientation and position of the camera. For our purposes, it will make it easier to keep the camera fixed in place and change the orientation of the sphere. This way, we can focus on the math without getting into the details of how graphics libraries are implemented. Let me zoom out and visualize a third-person perspective of our setup, because there is another important aspect of the coordinate system that affects how we rotate the sphere. A coordinate system can either be left or right-handed. The handedness of a coordinate system determines the positive direction of rotations in 3D space. To figure out whether our coordinate system is left or right-handed, we use something called the right-hand rule. This can be a bit tricky depending on the orientation of your axes, so let's change the orientation so that the z-axis points up. With your right hand, point your index finger in the direction of the positive x-axis, and your middle finger in the direction of the positive y-axis. Now, because the direction your thumb points is in the same direction as the positive z-axis of our setup, this is a right-handed coordinate system. If you try the same thing with your left hand, your thumb will point in the opposite direction of the positive z-axis drawn here. The interesting thing about left and right-handed coordinate systems is that they are reflections of each other. If we describe the same rotation in terms of the axes of the system, the rotation we see in the left-handed coordinate system will be in the opposite direction of the rotation we see in the right-handed coordinate system. Since we're using a right-handed coordinate system, we can use our right hand to determine the positive direction of rotation around an axis. I'll show you how to do this later. For now, let's resume viewing the scene from the same perspective we'll use throughout the rest of the video. Next, let's talk about what these red, green, and blue arrows are. In math, we call these basis vectors, and together they represent the coordinate system of the sphere. The basis vectors all have a length of 1 and are perpendicular to each other. What this means for our setup is there are two ways to write the coordinates of a point in space. For example, the coordinates of the blue vector that points up towards the north pole of Earth are written in terms of the sphere's coordinate system as 0, 0, 1. But we also write this vector in terms of the axes of our setup, like this. Given the current orientation of the sphere, the transform position of this vector has a negative x-coordinate, a negative y-coordinate, and a positive z-coordinate. We write the basis vectors of a 3D space with the letters I, j, and k. We even give them funny little hats to mean that they are unit vectors and have a length of 1. The basis vector I hat has the coordinates 1, 0, 0, j hat has the coordinates 0, 1, 0, and k hat has the coordinates 0, 0, 1. Let's change our setup slightly so that the basis vectors point out of the sphere, so it's easier to visualize its orientation. But you should still think about the basis vectors as having a length of 1 and whose tails sit at the origin. Later, we'll implement a function that calculates the transformed position of a point in space. This function takes in a 3D vector as input, where the components of the vector correspond to the coordinates of a point in 3D space. Given a vector like I hat as input, the function returns its position in terms of the external coordinate system of our setup. Similarly, we can pass in j hat and k hat as input to the function to calculate their transformed positions. In general, this is how we visualize the points that make up a 3D object in the transformed space, like the outline of one of the continents on Earth. It's also how we can verify that the Earth rotates in the manner we expect, by checking the positions of the basis vectors after we perform a rotation. But we're getting a bit ahead of ourselves. Now that we've established the coordinate system of our setup, let's take a step back. So far, everything we've discussed applies to whatever approach you take for rotating 3D space. Whether you're using rotation matrices or quaternions, it's important to consider what perspective you're viewing the coordinate system from, whether it's right-handed or left-handed, and how you represent the sphere's coordinate system as it rotates. We are going to rotate the sphere using the Quaternion number system. Think of quaternions as numbers you can perform operations on, like addition, multiplication, and exponentiation. For our purposes, we are going to use quaternions to do three important things. We represent the orientation of the sphere as a quaternion. We compute the transformed position of a point using the value of the orientation quaternion. And we represent rotations as quaternions and apply them using multiplication. When you look up the definition of the Quaternion number system, it looks like this. A quaternion is written as w plus xi plus yj plus zk, where w, x, y, and z are real numbers, and the constants I, j, and k have the properties I squared is equal to j squared, is equal to k squared, is equal to I times j times k, which is all equal to -1. If you're familiar with the complex number system, you'll recognize the complex unit I, which has the property I squared is equal to -1. This is the property that makes it so you can represent rotations in 2D space using complex numbers. Quaternions extend the complex number system by introducing j and k and these additional properties. Now, we could continue defining the operations of quaternions, like multiplication, using these algebraic properties from the definition. However, let's instead focus on the high-level features and leave some of the details for when we implement the number system. The quaternion representing the current orientation of the sphere has the value of 0.94 plus 0.17 times I minus 0.23 times j minus 0.17 times k. If we set this expression equal to the variable q, you can think of q as representing a single quaternion number. Later, we'll talk about where these values come from, but for now, know that this quaternion somehow encapsulates the orientation of the sphere. To transform a point using this quaternion, we perform the quaternion vector product. The point is multiplied from the left by the quaternion and from the right by its inverse. This operation converts the point from the sphere's internal coordinate system to the external coordinate system of our setup. There's more to say about why this works, but for now, this is the method we'll use. The last important thing that we want to use quaternions for is to express and apply rotations to the orientation. To rotate the sphere around an axis by an angle, we construct a quaternion that looks like this: the cosine of theta divided by 2 plus the sine of theta divided by 2 multiplied by the axis of rotation. To apply this rotation to the orientation, we multiply q from the left by the value of the rotation to get the resulting orientation. Let's switch over to a demo of the code we are going to write and look at how these features work together to rotate the sphere. Currently, I'm in a directory which contains a working version of the code we'll implement. In the source directory, we have a vector class, Quaternion class, and a unit test file. Let's start an interactive Python session and import the vector class as well as the Quaternion class. Next, let's construct a quaternion using the w, x, y, and z values of the sphere's current orientation. We'll also want to define some variables to represent the basis vectors of the sphere's space. To differentiate these from the quaternion units I, j, and k, let's include hat in their names. To calculate the transform position of one of these basis vectors, we call the transform method on the quaternion and pass in the basis vector as input. For example, to calculate the transformed position of I hat, we call transform on q and pass in I hat as input. Let's actually put this in a print call to show the coordinates of the resulting vector. Before I run this line of code, what do we expect the output to be? Given the current orientation of the sphere, the transformed position of I hat is in the octant where the x-coordinate is positive, y-coordinate is negative, and z-coordinate is positive. And when I run the line of code, these coordinates look correct. Let's also calculate the transformed positions of j hat and k hat. In general, this is the function from earlier, which converts the position of a point in the internal coordinate system of the sphere to the external coordinate system of our setup. Next, let's rotate the sphere to a new orientation. For example, let's say we want to rotate the sphere 90 degrees around the y-axis in this direction. First, we need to determine the positive direction of rotation for our coordinate system. Since we are using a right-handed coordinate system, we use our right hand to figure out the positive direction of rotation. When you stick your thumb out in the direction of the axis of rotation and curl your fingers, the direction your fingers curl will be in the positive direction of rotation. In this case, this is the same direction as we want to rotate, so our angle will be positive. We also want to express the angle in radians, so let's import the math library to define the constant pi. To construct a rotation quaternion, we'll use the method called fromAxisAngle. This method has two arguments, the axis of rotation and the angle in radians. Because we are rotating around the y-axis, we'll pass in the vector 0, 1, 0 for the first argument, and because we are rotating 90 degrees in the positive direction, we'll pass in pi over 2 for the second argument. This gives us the quaternion that rotates space around the axis by the angle. To apply the rotation, we multiply our orientation by the rotation from the left. When I print out the value of q, we get the value of the orientation after applying this rotation. And when we rotate the sphere on the left around the axis by the angle, we get the same value. If you're wondering how we compute the intermediate values between the starting and ending orientation, we'll get to that later in the video. For now, our implementation of the Quaternion class will focus on the basics. Finally, let's print out the transformed positions of the basis vectors to show that we are getting the expected output. Moving forward, I'm going to erase the x and y axes, since these will always be in the same place. Let's open a text editor and create a Quaternion class. The constructor takes in 4 floating point numbers to initialize the instance variables w, x, y, and z. To start, let's stub out the 3 methods we used in the demo. The static method fromAxisAngle takes in an axis and angle as input and returns the corresponding rotation quaternion. The multiply method takes in a quaternion as input and returns the result of multiplying this quaternion by the other quaternion. And the transform method takes in a vector as input and returns its transformed position according to this quaternion. Let's write some unit tests for our class. The simplest orientation we can describe is a quaternion with the value of 1. Let's also create some variables for the basis vectors of the space, which is how we test the orientation of the sphere. For example, when the orientation is 1, the coordinate system of the sphere and our setup are aligned. In other words, the transformed positions of the basis vectors are equal to their starting positions. Let's say we want to rotate the sphere a quarter of a rotation around the x-axis. We express this rotation using the fromAxisAngle method, passing in the vector with the coordinates 1, 0, 0 for the axis and pi over 2 for the angle. To determine which direction this quaternion rotates space, stick the thumb of your right hand out in the direction of the axis of rotation and curl your fingers. In this case, the positive direction of rotation is this way. When we apply this rotation to the orientation by multiplying it from the left, I hat remains in place, j hat rotates to the position 0, 0, 1, and k hat rotates to 0, negative 1, 0. Let's test another rotation. At first, this may seem like overkill, but there's a good reason why we should test 2 rotations. For the second rotation, let's rotate the sphere around the diagonal axis with the coordinates 1, 1, 1 by a third of a full rotation in the negative direction. When we apply this rotation to the current orientation of the sphere, the basis vectors rotate around the axis negative pi over 3 radians to these positions. What happens if we change the order in which we apply these 2 rotations, so we rotate by b and then a? Do we get the same orientation of the sphere as illustrated by the basis vectors? It turns out, if we apply the rotation b and then the rotation a, we'll get a completely different orientation. Let me show you with a copy of our setup. When we rotate around the diagonal axis by negative 2 pi over 3 radians, and then around the x-axis by pi over 2 radians, we get an orientation that looks like this. The fact that the order matters when we apply rotations to 3D space highlights a key feature of quaternions. Multiplication is non-commutative. Let's duplicate this test case and assert what should happen when we apply the rotations in the other order. First, we need to rotate our sphere back to the orientation of 1. When we rotate by b and then rotate by a, the basis vectors rotate to these positions. Next, let's write some simple tests for our multiplication method. When you consider that quaternion multiplication is non-commutative, the property I times j times k equals negative 1 is saying quite a bit more than you might first think. This property can be expanded into these variations, which demonstrate how the order of the units changes the result of the multiplication. Let's write some quick unit tests using these properties and call the test good here, so we can move on to implementing the Quaternion class. To implement multiply, we calculate the product of 2 quaternions by setting up the multiplication like this, and using algebra, expand and simplify the expression. I'm going to skip showing the full algebraic exercise here, but as long as you're careful to preserve the order of units when simplifying, you should get this expression. Instead, I want to highlight some concepts from linear algebra that appear in the product. When you consider the x, y, and z components of the two quaternions to make up vectors, then both the dot product and cross product from linear algebra show up in the quaternion product. This is made a little bit more clear using an alternative notation for writing a quaternion in terms of the scalar component w and the vector component v. Here we can see the negative dot product of the two vectors appears in the scalar component, and the cross product appears in the vector component of the resulting quaternion. If you're familiar with linear algebra, you'll know that both of these operators have useful geometric interpretations. The dot product of two vectors is related to the angle between them, and the cross product returns the vector perpendicular to the two vectors. Later, we'll use this feature of quaternion multiplication to rotate the Earth from user input by calculating the angle and axis of a rotation. The fact that quaternion multiplication subsumes both of these operations points towards the fundamental nature of the number system and how it encodes rotations. Let's implement the multiply method by returning a new quaternion whose components equal this expression, and run the multiply tests to make sure it works as expected. Okay, that looks good. We've successfully encoded the properties of the quaternion units, including their non-commutative nature. To implement the transform method, we calculate the quaternion vector product from earlier. First, we convert the point from a vector to a quaternion that has the same x, y, and z components, which I'll call p. Then we calculate the product, which I'll store in the variable t, by multiplying p from the left by this quaternion, and then from the right by this quaternion's inverse. Finally, we convert the resulting quaternion to a vector and return it. To understand how and why this method calculates the transformed position of a point, we need to talk about what's really happening in 4 dimensions with quaternions. Here we won't go into as much detail as the last video, but it's still good to know at a high level what's going on in this function, because it's the reason why we can think of quaternions as representing orientations and rotations in 3D space. It's also responsible for some of the quirks when using quaternions. Here's an overview of how this function works. Let's temporarily remove the sphere so we are left with the basis vectors of the space. To visualize a rotation, we express the value of q in terms of the angle and axis of a rotation. Let's visualize the rotation around the diagonal axis from earlier. This axis needs to be normalized, so we divide it by its magnitude to have a length of 1. In addition to the basis vectors, let's visualize what happens to the set of points that make up the cube whose sides are parallel to the axis of rotation. Here's the thing. In reality, quaternions describe rotations in 4 dimensions. These rotations are difficult to visualize, but we can see a partial picture of what's happening by modifying transform to no longer multiply by the inverse. When we visualize the rotation associated with this axis, there are actually 2 rotations that happen at once. One of these rotations does what we want. It rotates space around the axis by the angle. The other rotation also rotates space in relation to the axis, so that the points get rotated into the 4th dimension. Watch what happens to space as we rotate from 0 to 2 pi. One of these rotations rotates space around the axis in the direction according to the right-hand rule. The other rotation oscillates the points back and forth along the axis. When we highlight the face of the cube perpendicular to the axis of rotation, watch how points in this plane rotate around the axis according to the first rotation, and also along the axis in this oscillating motion. The big limitation of this setup is that it's a partial picture. We only see the x, y, and z components of a point in space, and we can't see the 4th dimension represented by the w component. That said, it's enough to illustrate the key idea behind the transform method. The way transform works is by preserving the rotation that we want, and canceling out the other rotation. For example, let's say the angle of rotation is pi over 3 radians. When we multiply by q from the left, this rotates space around the axis by the angle, and also rotates space along the axis and into the fourth dimension. We reverse this second rotation by multiplying by q's inverse from the right. This also applies two rotations. The first rotates space around the axis by the angle again, and the second rotation reverses the unwanted rotation. Now, why does multiplying by the inverse preserve one rotation and cancel out the other? Let's go ahead and implement the inverse method. The inverse of a quaternion is equal to its conjugate divided by the norm squared, where the conjugate is equal to the quaternion with the x, y, and z components negated. To implement this, create a variable called norm squared, which is equal to the sum of the squares of the w, x, y, and z components, and return the conjugate divided by the norm squared. The defining property of the inverse is that a quaternion multiplied by its inverse equals 1. In other words, the inverse of the rotation quaternion performs the same 4D rotations, but in opposite directions. Let's visualize the rotations represented by the quaternion on the left and its inverse on the right. When we play the rotations at the same time, the direction of the rotations are reversed. For the first rotation of the inverse, the points clearly rotate around the axis in the other direction. But for the other rotation, it's difficult to see how it's reversed. Imagine I only show you the x component of a point rotating around the origin in the xy plane. What you see is the point oscillating back and forth along the x-axis. When the direction of the rotation changes to rotate in the opposite direction, the point still appears to oscillate in the same manner, even though the direction is different. Change the x-axis to be the axis of rotation, and the y-axis to be the fourth dimension, and this is what's happening in our setup. If you focus on the points, like those in the highlighted face of the cube, even though both faces appear to be oscillating along the axis of rotation, the points on the left are rotating one way, and the points on the right are rotating the other. The key insight behind the transform method is that when we change to multiply from the right by the inverse, this changes the direction of the first rotation around the axis, but crucially doesn't change the direction of the second rotation along the axis. This means when we left multiply by the quaternion and then right multiply by its inverse, the rotation we want is preserved and the other rotations cancel each other out. In its essence, this is how the transform method works. When we perform both multiplications at once, space rotates around the axis by twice the angle represented by the quaternion, which is why we divide the angle by 2 when expressing a rotation. We could spend a lot more time talking about what's happening in 4 dimensions, but instead, I'll link to some resources that I found helpful in the description. My hope is that the explanation here gives some notion of how a quaternion and its inverse work together to rotate 3D space, and that a byproduct of this operation is that rotations are doubled. Let's go back to visualizing the sphere and implement the final method of the Quaternion class, from axis angle. To start, let's create a variable called half angle to store the angle divided by 2. Then, we'll return the quaternion, which represents the rotation. This rotation has a w component that is equal to the cosine of the half angle, and x, y, and z components that are equal to the sine of the half angle multiplied by the axis of rotation. Let's run our test suite to make sure we've implemented things correctly. And it looks like we're failing our rotation tests. The reason we're failing these tests has to do with the length of the axis of rotation. When we constructed the rotation around the diagonal axis, 1, 1, 1, we passed in a vector whose length was greater than 1, causing the ratio of the angle and axis to get thrown off. To fix this in the from axis angle method, we can make sure the axis of rotation is normalized. Now, when we run the tests, they pass and we have a working quaternion class. It's important to know the quaternions we are working with are unit quaternions. In other words, a rotation quaternion expressed in terms of an axis and angle has a length of 1. That said, the way transform is implemented will still work for non-unit quaternions. Any scaling introduced by left multiplying by the quaternion is undone by multiplying by its inverse. When you know you are exclusively working with unit quaternions, which is typical for 3D rotations, you can use the conjugate instead of the inverse in the transform method, because the conjugate and the inverse are equal for unit quaternions. The quaternion operations we just implemented give us the tools we need to implement the first feature of our application. The way this feature works is when a user clicks and drags, we rotate Earth according to their mouse movement. To start, we want to map the 2D position of the mouse to a point on the sphere. The function I'm using maps points inside a radius onto the sphere and points outside of that radius onto a hyperbolic surface. Here's the code if you're interested. The important detail of this function is that the user can click and drag anywhere on or around the sphere. When a user clicks and drags to rotate the sphere, we keep track of 2 points on the sphere that correspond to the starting and current position of the mouse. Every time the mouse moves while dragging, we calculate the rotation that rotates a point from the starting position P1 to the current position P2. This involves finding the quaternion with the angle and axis that performs this rotation. The user should be able to rotate the sphere for any given orientation. Each time a rotation starts, we store the starting orientation and apply the rotation to it to calculate the current orientation. How do we calculate the angle and axis of the quaternion that rotates a point from P1 to P2? The answer is surprisingly straightforward. We represent the 2 points as quaternions and multiply them to get something that is almost the rotation we want. What this looks like is we write P1 and P2 as quaternions, whose W components are 0, and whose X, Y, and Z components are equal to the corresponding coordinates on the unit sphere. Let me also write the points as vectors, V1 and V2, because we're going to use linear algebra to explain how this works. As we saw earlier, when we multiply two quaternions, the dot product and cross product of their vector components show up in the result of the multiplication. Since the W component of these quaternions is 0, we get the negative dot product for the scalar component and the cross product for the vector component. Now, the dot product is related to the angle between the two vectors. Specifically, the dot product of two vectors is equal to the length of the vectors multiplied by the cosine of the angle between them. And the cross product returns a vector perpendicular to the two vectors. When you think about it, this vector must be the axis of rotation because when you rotate a point from P1 to P2, the point travels in the plane formed between the two vectors. The axis must be perpendicular to this plane, otherwise it wouldn't be possible for the first point to reach the second point. There's also a geometric formula for the cross product of two vectors. The length of the vector returned by the cross product is equal to the lengths of the vectors multiplied by the sine of the angle between them. In our case, we're projecting the points onto the unit sphere, so the vectors have a length of 1, making the dot product equal to the cosine of the angle and the length of the cross product equal to the sine of the angle. That is all to say, the product of these two quaternions gives us a rotation quaternion that is almost what we want. The difference is the dot product is negative, and the angle that corresponds to this quaternion is twice the angle that we want for the rotation. We certainly could use this result to get the rotation we want, but let me show you how we do this using the operations of quaternions. If we change the order of the multiplication and multiply by the conjugate of P1 instead, then both the dot product and cross product are positive. Now, all we need to do is divide the angle by 2, and we can do this by raising this expression to the power of 1 over 2, which has the effect of halving the rotation. This results in the rotation quaternion, which rotates a point from P1 to P2. When a user clicks and drags the sphere, we calculate this rotation on the fly using the 2 points on the sphere and apply it to the previous orientation to get the current orientation. And this works for any orientation of the sphere. Each time a user clicks and drags, we rotate it using the position of the mouse. The Quaternion class we implemented provides all the operations needed for this feature, except for a power method. We're going to skip writing code for this feature because some of it depends on the environment you're working with, but this should give you a pretty good idea of how it's done. That said, I'll make sure to link some example code in the video's description that includes a power method. Let's discuss how to implement the second and last feature of our application. The way this feature works is, when a user presses the spacebar, we record the current orientation of Earth, and after they rotate the Earth around for a bit, they can press Enter to rotate back to the recorded orientation. Let's switch to viewing the orientation of the spheres using the values of the Quaternions and the basis vectors of their spaces. As we prepare to implement this feature, it's important to recognize that the Quaternions we are working with are actions. To be precise, the action a unit Quaternion describes is a rotation defined by an axis and angle. We want to solve for the rotation that rotates the sphere between the two orientations, and also generate the values of the orientation between the start and end of this rotation. To start, let's model this rotation with the formula r multiplied by q1 equals q2, where r represents the action which rotates from q1 to q2. Before we solve for the rotation, though, consider how all three of these unit Quaternions represent rotations. We can visualize one of these rotations by changing the orientation on the left to be 1. This is how a unit Quaternion represents orientation. It's the action which rotates the sphere from the standard position of 1, shown on the left, around the axis by the angle to the orientation on the right. Let's reset the left orientation to 1 and draw the axis of the rotation. Watch how the axis of this Quaternion changes as the sphere rotates to different orientations. And when we apply the rotation, the sphere rotates around the axis by the angle between the orientations. Each of these Quaternions describes a distinct rotation. In a right-handed coordinate system, we read these rotations right to left. To get to the orientation described by q2, first apply q1 and then r. This is why we left multiply by a rotation to apply it to the orientation. In our case, we want to solve for the rotation represented by r. To do this, multiply both sides by the inverse of q1. And as a result, the rotation is equal to q2 multiplied by the inverse of q1. This is the unit Quaternion which rotates between the two orientations. To generate the values of the orientation between the start and end of this rotation, we could change the value of theta from 0 to the angle of the rotation, and use this to compute the values of the orientation. But there's a cleaner way to do this that involves exponents. Think about the action a unit Quaternion represents. For example, to rotate around the z-axis by 90 degrees, we multiply the orientation by the value of this rotation Quaternion. To rotate 180 degrees around the z-axis, we can apply this rotation twice, which is the same as raising the rotation Quaternion to the power of 2. Conversely, to rotate by 45 degrees, we can raise this Quaternion to the power of 1 over 2. In general, to calculate the value of the rotation between the start and end of the rotation, we raise the rotation to the power of t, where t is a number that goes from 0 to 1. This is how we interpolate the value of the Quaternion between the two orientations. For each value of t between 0 and 1, we calculate and apply this fraction of the full rotation to the starting orientation to get the intermediate orientation. This is how we use the rotation we calculated to interpolate between the two orientations. We raise the rotation to the power of t and multiply it by the starting orientation. This is how we rotate the sphere between the orientations and generate the values of the orientation for each value of t between 0 and 1. This method commonly goes by the name SLIRP, which stands for spherical linear interpolation, because it generates the values that rotate the sphere at a constant angular rate. There are a couple variations of SLIRP. The version we have here uses exponentiation, but there is another geometric formula that looks like this. But before we celebrate, there's something you should know about how orientations are represented. Because the transform method doubles the angle of rotation, which is the reason why we divide the angle by 2 when expressing a rotation quaternion, there are actually two different quaternions that describe each orientation in space. To demonstrate this, let me change the orientations of the two spheres to be the same. When we rotate the sphere on the right around an axis by a full rotation, such as the y-axis, we get the other value which describes the same orientation. The difference between the two is the signs of the components are flipped. The fact that space is double covered is actually quite useful for animating between orientations. Here, let me show you by rotating the sphere on the right a little bit around the y-axis. When we interpolate the values between the orientations, the sphere rotates like this around the axis. Watch what happens if we change the quaternion to the other value which describes the same orientation, and then interpolate between them. Now the sphere rotates along the shorter path between the two orientations. We can use this to our advantage when implementing this feature. Before interpolating the values of the rotation, check which of these two quaternions is closest to our starting orientation, and pick the one which ensures that we will always rotate along the shortest path between the two. This is usually the default behavior for implementations of Slurp. And with that, we've implemented a basic Quaternion class and demonstrated how Quaternions provide a practical and elegant solution for 3D rotations. I'll add a link in the description of this video to a repository containing the code we implemented, as well as some example code for the two features. If you enjoyed this, please consider sharing it. And if you would like to support future videos, it would also mean a lot to me if you consider joining the Patreon.